That was my beautiful face at the start of the video, just to make sure the thing was on. Hi guys, Jerry again back. This is lecture 11, I think, in our ongoing series. So, and today I want to talk to you about what are called eigenvalues and eigenvectors. So it's this is when again, happy days when I was a lad and I was doing this in college. I had no idea what this was about, and I'm going to try and convince you that this actually does make some sense. Okay, first, and then I'm going to show you how to calculate eigenvalues and how to calculate eigenvectors. Now, this looks very mysterious, but again, surprisingly, there are many situations in engineering analysis where you have to calculate, or people do calculate eigenvalues and eigenvectors to get some information about how the system is behaving. So there is some practical application of this, although we're not going to do that practical application. I'm just going to teach you the recipe and teach you not to be afraid of this stuff, because as I say, when I was at your age, I was very fearful and I had no friends, and I suppose that kind of was a vicious circle then, and the fact that I had no friends kind of accentuated my fearfulness. And but you shouldn't be fearful, because this is all right actually. And here's the basic problem, right? So we're going to look at a 2x2, or you can look at 3x3. Again, it's a square matrix, and we're going to multiply square matrices by vectors. Okay, so you can just pick a vector. So I just picked this example here, 5, 6, 2, 1, as an example. And I'm going to multiply the 5, 6, 2, 1 by just, it doesn't matter. Let's pick 4, 4. Okay. Now, as I said to you, when I was, again, I forget how easy when I was, because I've been doing this for 40 years now. I've forgotten how little I knew when I began. So I want you to just be very comfortable. If you're multiplying a square matrix by a vector or a column vector like that, you're going to get another column vector. And that's a very important thing. If nothing else in this little video series of lectures, remember that. A square matrix by a column vector gives you another column vector. So if you look at this situation, and this is how this arose, guys, or people are messing around with this, matrices and multiplying matrices together. Now, these are mathematicians, again, like myself, with no friends and very little social life. So this is what you do, right? So you got a square matrix, multiply it, and see what happens. In this case, what you do when you multiply this, you get on the top there, you get 5 by 6, or 5 by 4, which is 20, plus 6 by 4, which is 24. Right, so it's 5 by 4 plus 6 by 4. And on the bottom, you get 2 by 4, which is 8 plus 4. So you get, what's that? That's 44, and you get 12. And if you like, you see, look, there's a 4 common. So what, again, mathematicians, again, no friends, you can bring the 4 outside if you want to, and write that as 11, 3, but that's not important. Although, you can do it. That's fine. And you can do something similar here. Look, I'm going to do, 5, 6, 2, 1 again. And let's have a minus number. Ooh, minus 4 and 5. Doesn't matter. And when you do that, guys, again, here, you're going to get a column vector again. On the top one, you're going to get 5 by minus 4, which is minus 20, plus 6 by 5, which is 30. And on the bottom, you're going to get 2 by minus 4, which is minus 8, plus 5. And on top, then you're going to get 10, and the bottom you get minus 3. All right. So far so good. So again, what I want to emphasize to you guys in this kind of setup is the operation. You're multiplying a square matrix by a column vector, and you're going to get another column vector. Now, this is not obvious, but it is true sometimes. Typically, when you're multiplying a square matrix by a column vector to get another column vector, in an engineering system, typically, this represents your input. This represents your output. And this is somehow a matrix representation of what the system is. All right, so this is very kind of, again, this is not obvious at all, that this is what's going on. But a lot of the time, when you're doing matrix multiplication, that's what you're doing. You're inputting something, in this case, a matrix, a column vector, into a system which is represented by a square matrix, which is pretty typical. And when you input that, you're getting your output, which is the same form as the input, but different numbers. Okay, so basically what happens is that the system changes your input into your output. All right, so this is very general now and very kind of wave your handsy and maybe nonsense, but this is typical of what's going on. Okay, so this is the reason really why you're doing this kind of stuff, is you're inputting something here, represented by a column, into a system, represented by a square matrix, and the system converts the input into the output. Okay, so if you input 4, 4, for instance, into this system, you're going to get 4412 as your output. Boom, boom. Okay, so that's basically it. And if you input minus 4, 5 into the system, you're going to get 10 minus 3. All right, so that's fair enough. Now, I probably won't ask you matrix multiplication in that kind of context, but there it is. I might do, but I probably won't. Okay, so that's the first thing. Now, boys and girls, here's where it gets to me, and maybe not to you, but here's where it got interesting for mathematicians. If I multiply 5, 6, 2, 1, say, by this vector, let's multiply it by 1 minus 1. Okay, let's do that, right? Again, that's all we're doing. We know we're going to get a column vector as our output. So let's do that here. So you multiply the top one, you get 5 by 6, or 5 by 1, which is 5, minus 6 on top, and you get 2 minus 1 on below. And so on top here, you get minus 1, and you get 1. Now, so if I input 1 minus 1 into the system, I get minus 1, 1 as my output. Now, you can represent this, though. You can see the minus sign here? You can represent this another way. You can bring the minus sign out. So I can write this then as minus 1 into 1 and minus 1. Okay? Because if you multiply minus 1 by minus 1, you get plus 1. So all I'm doing here now, guys, is I'm kind of rewriting the output by just pulling a number outside. In this case, I'm putting the minus 1 outside. In the same way as you look at the first case situation here, I just pulled the 4 out. But now if you look at this particular input and this particular output, you see there's something kind of magical in a mathematical context is happening here. Because what's happening here is that your input is essentially the same as your output, except it's being multiplied by a number. So this is a very, very important kind of, so this input and this output and this number here are kind of intimately connected. It gives you a lot of information about what's happening in the system. Because basically what's happening is that your input here, 1 minus 1 is your input, is being magnified or diminished by a number, in this case, minus 1. All right? So you're taking an input and you're just taking, your output is essentially the same as your input, except it's been diminished. It's been either magnified, or it's been diminished, or it's been reduced by the number here multiplying the vector. So when your input and your outputs are related like this, you have what are called eigenvalues and eigenvectors. So in this case, your eigenvector is 1 minus 1, and your eigenvalue is minus 1. Okay, let's do another example as well. Now, I know this is very confusing, and I probably didn't explain this very, very well. But this is what happens. So there are some vectors, when you put them into the system, you essentially get the same vector as your output, except there's a magnifying factor. There's a multiplication factor. In this case, the multiplication factor is minus 1. Let's do another example. Exactly the same matrix here. Okay. Now, this doesn't always happen. It happens very, very rarely. And because it happens so rarely, the vectors that this happens for are very special. Let's do this one. 5, 6, 2, 1 multiplied by 3, 1. So on top here, you get 15 plus, so you get 15 plus 6. And on the bottom, you get 6 plus 2. No, you get 6 plus 1. It's not right. Sorry. Because 1 multiplied by 1 is 1. Okay. You know, if you did this in the exam, if you wrote down 2 there in the exam, I would be calling my children in and laughing at you, you know. So, but I'd be, you know, this would be, I would be guffawing at how stupid you are. But when I do it, apparently it's okay. I can make mistakes, but you can't. All right. So this is, so you get 5 by, let me make sure the top line is correct. 15 plus 6, that's correct. And 6 plus 1, which is correct. And so if I multiply that out there, guys, I get 21 and 7. And there's a common factor here. You see the common factor, which is 7. Whoa. So again, in this case, what's happening, so these vectors, the 3, 1, that vector 3, 1 is a very special input into the system, because when I get look at the output, I see I get the output again. The output is again the input, which is 3, 1, multiplied by a single number, multiplied by this kind of magnifying factor. So basically what this is kind of an application factor, essentially. So I'm taking the signal here, 3, 1, and it's being amplified by the number 7. And the way you do amplification engineering is you multiply. Okay, so the input signal in this case is being amplified by the number 7. Okay, so because you have this special relationship, this happens very, very rarely. Okay, and because it happens so rarely, these vectors or these inputs and these outputs have their own terminology. This input, and then because it happens so rarely, is what's called an eigenvector. And this number here, the number that you multiply the input by to get the output, is called your eigenvalue. Now this happens really, really rarely, folks. It happens. It doesn't happen. It happens. It's a drop in the ocean in terms of your inputs. Like for instance, if again look at just 5, 6, 2, 1, and if I multiply that by 7, 3, say, what you get here is 35 plus 18 on top, and you get 14 plus 3 on the bottom. So that gives you 53 on top, and it gives you 17 on the bottom. And there's no common factor there, I don't think. By 3, no, there's no common factor. So it's 53, 17. That's it. That's what it is. You can't write 53, 17 in terms of a number multiplying 73. Okay, so 73 is not an eigenvector. And almost all your inputs are not eigenvectors. But there are some inputs which are. And because they're special, they have their own name, and they're called eigenvalues and eigenvectors. And as I say, this gives you a lot of information about the system. The eigenvalues of a system are very, very important. They tell you a lot about what's happening in the system. Once you know what the eigenvalues are, you know a lot about what the system is, basically. And that's the reason why this stuff is so important. All right, so that's the kind of introduction. Now what I want to do is I want to kind of generalize this, folks, if I could. I know you're going to hate me to do this because you don't like when I generalize things, but this is the difference between secondary school and college. In college, you always want to generalize. You want to write things that are true for every situation, not just for one specific situation. Because if you look at this situation here, we talked about 2 by 2 matrices multiplying by a 2 by 1. Okay, now I'm going to just generalize this and give you a general definition what an eigenvalue and eigenvector is. Okay, so this is the general definition. So let A be a square matrix. Then X is an eigenvector with eigenvalue A, and the eigenvalues usually in mathematics are denoted by the letter lambda. This is just tradition, where I think this was Euler came up with this. Then X is an eigenvector with eigenvalue lambda if and only if, again, this is just mathematical jargon. Here's what the definition is. Ax is equal to lambda x. Whoa, you're afraid now, I bet you. Now you're sorry you got up in the morning. So yeah, so this is what's this is in general. So A can be any square matrix. Okay. So in this case, if I can go back to my example here, up here, A is 5, 6, 2, 1, and your X is 3, 1. And that's all it is. So we're just generalizing this. So we're not just confining it to 2 by 2 matrices. We're saying any square matrix can have this property. And so as I say, folks, what's happening here is that X is your input to your system, which is modeled by a square matrix. And what you're getting is basically the same. The output is on the right-hand side. The output is essentially the same as the input, except you're multiplying it by a number. You're magnifying it by a number. So if you think what what an amplifier is, a physical amplifier is you take a noise signal and you put it into your system, And what you get is you get the noise magnified, and the magnification factor is called lambda. So, but in mathematics, we don't call it magnification factor, we call it an eigenvalue. So this is the definition of what an eigenvalue and eigenvector is. Now, boys and girls, when I did this the first time, I did not go for this at all, but you should go for this because this is actually very easy. The actual recipe is very easy. I tried to motivate what's going on, and that's kind of the motivation is kind of important because this is a kind of a typical situation that you see in mathematics. Okay, now right now this next thing I'm going to do now is I'm going to take this equation here and I'm going to mess around with it and do something to it and show you how to calculate eigenvalues and eigenvectors. Okay, so don't be afraid now. Just let's go with this now. So I'm calling I be the identity matrix. Now, I has some nice properties. Remember we talked about this. If you multiply a square matrix by I, like this, it's exactly the same as multiplying by I by A. You just get A. So the identity matrix is really cool because if you have a square matrix and you multiply by the identity, either to the right or to the left, you always get back to what you started with. You get the square matrix. It's also got a very important property when you're talking about column vectors. Okay, so here's 2. X is a column matrix. If you multiply I by X, you're going to get X. But it doesn't work the other way because you can't do Xi. You can't do that because let's say this is a column vector with n rows and 1 column, and this is n by n. So you see here, folks, that these two numbers here are not the same. So you can't do this. You can't multiply x by I, but you can certainly multiply I by x. And when you multiply I by x, you always just get x. Okay, so be a little bit careful. This identity matrix, and when I was again your age, folks, this difference kind of caught me out a little bit. I never really went for it until I just got used to using this nonsense. But when you've got an identity matrix, you can multiply any square matrix either before or to the right or to the left, and you still get A. But you have to be a little bit careful with columns. It only works when the column is on the right of A, because x multiplied by I here makes no sense. You can't do it because this is going to be n rows and 1 column, so it's n by 1. This is going to be n by n because it's n rows and columns, and because these two numbers here are not the same, you can't multiply x by I. But you certainly can multiply I by x, okay? And if you do that, you get x. And the reason why this is important is because of the next thing I'm going to do, okay? So stay with me here. Hold on to your hats here now because this is going to be tricky. Don't be afraid. You're in good hands here. Okay. All right. So let me just write this down. So this is the definition of what an eigenvalue and an eigenvector of the matrix A is. Okay, so A is the basic vector that you're talking, or the matrix that you're talking about. If you have this situation, AX is equal to lambda x, then x is called an eigenvector of A, and lambda is called the eigenvalue of A. Now, boys and girls, remember I can say, if I can write this thing here as, I can do that because of this. If x is a column matrix, then I by x is equal to x. So all I've done here now, guys, is I've replaced x by ix. Okay. Now I'm going to bring this. So this is a this is still a column vector. So don't be worried about this. This is still a column vector. But I'm going to bring this over to the other side, just for the laugh. So therefore, ax minus lambda I x is equal to 0. And I put a bar under the 0 because it's a vector column with zeros in it. And so this is, this could be, if A is a 2 by 2, this is going to be 0, 0. If A is a 3 by 3, it's going to be 0, 0, 0. And because of that, then it's going to be 0 with a bar under it. Now, if you look at the left-hand side here, guys, you see there's a common term. There's an x on the right here, and there's an x on the right here. So what you can do is you can bring that outside. So therefore, you get A minus lambda I x is equal to 0. And that's okay. Now, you may be a little bit hesitant in doing that because you're not used to multiplying matrices, especially this kind of general form. But that is what you can do. So this is exactly the same as that. Now, boys and girls, here's where it gets a little bit tricky now. This, if you think about it, is a simultaneous equations. So there's n equations in n unknowns. Okay, this is what this system, this thing here, a minus lambda I x is actually n equations in n unknowns, where the unknowns are what the components of x. You don't know what x is. That's what you're trying to find. So this is a set of simultaneous equations, n simultaneous equations in n unknowns, which are the components of x. Now, we'll see here, guys, that this is a special system of simultaneous equations. The right-hand side is 0. So this is n equations in n unknowns, but it's a homogeneous. Remember we talked about this? I can't remember when we talked about this, but we talked about this before. If the right-hand side is all zeros, you have a homogeneous system of simultaneous equations. Now, again, you need to go back and look at the lecture. This is not obvious, but this is very common when you do this. Because you've got zeros on the right-hand side, if you want non-zero solutions to x, the determinant of this must be equal to 0. So therefore, what you must get is the determinant of a minus lambda I, that must be 0. And that equation, the determinant of a minus lambda I, is called the characteristic equation. Oh my God, guys, this is beautiful. Characteristic, I don't know if that smells right, equation. Oh my God. So it's the determinant of a minus lambda I equals 0 is a characteristic equation. And basically what this equation is, folks, is an equation for lambda. Because you know what a is, you know what I is, you don't know what lambda is. This equation is going to tell you what lambda is. And once you know what lambda is, you can find out what x is. All right, so this is all just, this is very scary mathematical stuff. And you're all very afraid, but don't be afraid, okay? Now, can I just point out the difference between this 0 with a bar under it and this 0? This is the number 0, whereas this is a vector of zeros. Okay, this is a 0. This you're going to get an equation. So let me just show you how to get the eigenvalues of a 2x2 matrix, and we're going to stop here today, I think. Okay, because this is horrendous, but this is very good. Get on top of this now, and don't be afraid, because you will be seeing this later on, and you'll be saying, "Oh, that guy Jerry, great looking guy, but he just didn't teach us this properly at all." I'm teaching properly now, so just listen. This is all very fine, and this is what's going on. This is the reason why we're doing what we're going to be doing. But from your perspective, guys, from an exam perspective, mostly what I'll be asking you is I'll be giving you a square matrix and asking you to calculate the eigenvalues and the eigenvectors. That's it. And let me show you how to do it. It's actually very, very easy. Okay. So, guys, I'm just going to peer over the edge here. Don't be afraid. Again, just to make sure this thing is still working. All right, seems to be okay. So, let's do this. So, here's a question. Calculate the eigenvalues of, let's look at the matrix we started off with, 5, 6, 2, 1. Okay? Now, if you're looking back in past exams, this question crops up a lot. Okay, so you probably will be asked. Guys, I can't remember what we put on the exam, especially with the. I can't remember what Connor told me to put on the exam, because Connor is the boss. I can't honestly remember, especially with the virus nonsense. I don't know what we're doing. Yeah, but this, if you look back at past exams, this is it. And when I was your age, I was always a bit wary of this because I didn't really understand what's going on. It doesn't matter if you understand what's going on or not. You need to remember what the recipe is. All right. So just follow this. Don't be afraid. and it's actually not too bad. It really is. Okay, so here's what you do. Here's how you calculate the eigenvalues. Okay, so you take your matrix. Here's the solution. You take your matrix. Okay, write down the numbers, square matrix again. Now we're going to get a determinant. So you put the coefficients into a determinant. Now here's the magic, folks. You subtract lambda from the main diagonal. Okay, so you put minus lambda next to the 5, and you put a minus lambda next to the 1, and you set that equal to 0. That's it. That's all you do. That's it. To calculate the eigenvalues, that's what you do. You get the determinant of a 2 by 2 matrix, because we've got a 2 by 2 system up here. You subtract lambda from each of the main diagonal elements. You leave the 6 and 2 alone, and you set it equal to 0. So let's look at this. Let's multiply this out. So what you're getting a 2 by 2 determinant, you multiply this by this. So therefore you get 5 minus lambda by 1 minus lambda minus 12 is equal to 0. Okay? Multiply that out. You get 5 plus lambda squared minus 6 lambda, I think, minus 12 is equal to 0. So therefore you get lambda squared minus 6 lambda minus 7 and 1 to say is equal to 0. Yeah? So you get lambda squared minus 6 lambda minus 7 is equal to 0. And if you look at what you end up with, folks, is you end up with a quadratic equation for lambda. And the reason why it's quadratic is because your square matrix that you started off with is a 2 by 2. If you had a 3 by 3 matrix, you're going to get a cubic equation in lambda. If it's a 4 by 4 matrix, you're going to get a quartic equation in lambda, etc., etc., etc. So the bigger the matrix, the bigger the square matrix, the more complicated. This is what's called the characteristic equation. So this is the characteristic equation. So the characteristic equation in this case is a quadratic equation because you started off with a 2 by 2 matrix. Lambda squared minus 6 lambda minus 7 is equal to 0. Now, guys, I want to factor that. I think, can I come over here? Can I factor that easily? Is it lambda plus 1 by lambda minus 7 is equal to 0? I just factor this in my head. Oh, this is real-time mathematics in front of you guys here. I think that works. Okay, so lambda squared, now you can use the quadratic formula as well, of course, but I think you can factor this pretty straightforwardly here like this. So you get lambda plus 1 by lambda minus 7 is equal to 0. So therefore, lambda plus 1 is equal to 0. So you get lambda is equal to minus 1. Or lambda minus 7 is equal to 0, or lambda is equal to 7. So in this case, you've got two eigenvalues. The two eigenvalues are minus 1 and plus 7. What do you think, babies? What do you think? Are we going for this? This is good, isn't it? Yeah, no, this is very easy. It really is. It's that easy. And that's the recipe. When I was your age, again, I was very resistant to recipes. Like, what am I really doing? It doesn't matter what you're really doing. That's an existential question. What are you really doing? Just do it. Just do this. Okay, take the square matrix, write it down, subtract lambda from the main diagonal elements, get the term set equals 0, because that's what you do. Let's do another one. And I think we'll stop here and we'll continue again tomorrow. And then we'll do 3 by 3 matrices tomorrow. Ooh, and then we'll start looking at eigenvectors. Okay, so let's do another one. And just because we're here, let me do one in the book. Another one in the book. Okay. And as I say, guys, this is an important. Next week, maybe, or the week after next, just before we finish, I'm going to go back maybe and go through last year's exam and show you how easy the stuff is, especially my stuff, how easy it is. But there is a lot of it. Okay, that's the problem. So let's do another one. Eigenvalues. Oops, sorry. Can I call it eigenvalues for this matrix here? 7 minus 2, 1, 4. Okay. So eigenvalues for 7, 2. Guys, I'm going to just check that you can still see that. You can maybe. Let me put it up here because I just did this stupid thing here. Okay. So eigenvalues for 7 minus 2, 1, 4. Suppose you're in the exam and you're asked to do that. Okay. The actual recipe is very, very easy. And this is what you need to remember. Just remember this. Why you're doing this, I can explain why you're doing it, but you don't have to even remember why you're doing this. Just remember what the recipe is. So here's the solution. So you take your numbers here, folks. You put two straight lines there because you wanted to get the determinant. It's 7 minus lambda, and it's 4 minus lambda, and it's minus 2, and it's 1, and you set that equal to 0. Because that's what you do. Just do it. Okay? Then you get the determinant of this 2 by 2, so it's 7 minus 4 by 4 minus 1. Therefore, now be careful here, this is minus 2 by 1, which is minus 2, but it's minus, so it's this by this, minus this by this, so this gives you plus 2 is equal to 0. Be very careful with the minus signs here, folks, because typically in the exam, people screw this up. Because remember what the determinant of 2 by 2 matrix is. It's this by this minus this by this. And this by this in this case is minus 2, and minus by minus gives you plus. So when you multiply that out, guys, you'll get 28 plus lambda squared minus 11 lambda plus 2 is equal to 0, I think. So therefore you get lambda squared minus 11 lambda plus 30 is equal to 0. Okay. Oh, guys, I think I can fact this in my head because I'm just so bloody good. Look, I think this is 11 minus 5 by 11 minus 6. Yeah, it is. Oh, God. Oh, I'm the world's greatest mathematician, I think. Yeah, because I can factor this in my head. So this is what I think this is what that's what you get. And so therefore, folks, you get lambda equal to 5, 5 or 6. So it's lambda is equal to 5 is one solution, lambda is equal to 6 is another solution. Okay. So your two eigenvalues in this case are 5 and 6. This is your characteristic equation here. Again, it's a quadratic equation because it's a 2 by 2 matrix, and you get 5 and 6 then as your two values, your two eigenvalues. Now, once you've got the eigenvalues, you can get the eigenvectors, and we'll talk about that tomorrow. And we'll do maybe a 3 by 3 kind of calculation tomorrow as well. Get the eigenvalues for 3 by 3 matrix, which is a little bit tricky because you're talking about a cubic equation, which are difficult to satisfy, which are difficult to solve. You have to, guess one of the solutions, if you remember from secondary school. But we'll do it tomorrow. We'll start off with that, and then we'll start looking at calculation of eigenvalues and eigenvectors. But for this morning, guys, if I ask you for the eigenvalues of a 2 by 2 matrix, this is all you do. Come on. There's marks. Here's 3%. Come on, just take the marks and get into second year. All right, that's it. And so I'll talk to you again tomorrow. Okay, guys, thank you, and stay safe, be nice to everybody, and be positive. I know this is probably getting on your nerves now at this stage, but just, it's going to be over. Let's hope there is an over to this, and we'll get back together again soon, all right? All right, talk to you later. Be good, bye. Yep.